Swayam Prabha. Digital India. Educated India.
Hybrid friction stir welding. So, after conventional friction stir welding processes also having some advantage and disadvantage as well. So, modifying the conventional friction stir welding process, hybrid friction stir welding process has been developed. So, hybridization means it is a simple way by adding some extra heat source with the conventional friction stir welding process that actually brings some new dimensionality that is called the hybrid friction stir welding process. So, in this case the hybrid friction stir welding process normally comes into the picture in the by looking into the two different aspects. One is if the material workpiece material is very hard, or if the workpiece material is thermal conductivity of the material is very high, and both the cases using the conventional friction stir welding process little bit having some demerits of. So, to overcome that kind of things, so hybrid friction stir welding has been developed, but hybrid friction stir welding is advantageous specifically for joining of the dissimilar materials, because here there is a scope of controlling the intermetallic formation that is very much difficult in case of conventional fusion welding processes, or maybe I can say the conventional friction stir welding process as well. So, let us look into how this hybrid friction stir welding looks like. So, here if you see the FSW is developed in combination with the secondary energy source, and it can be used both for similar as well as dissimilar materials. In similar materials the configuration is like that. We use the conventional friction welding tool, that means the tool shoulder is in contact with the workpiece surface as well as the pin in depth, that is also in contact or steering action of the materials. But if it is very hard, then if we use some extra heat source that actually basically soften the materials and make easier the plasticization of the material and can expect a very good weld joint. So, in this case for joining of the similar kind of materials there is no need of using any kind of tool offset or maybe offsetting of the energy source. We just straightforward along the weld central line we can simply put that secondary energy source and then it helps to joining of the similar materials, but relatively harder materials. Here relatively harder material in the sense that normally we define, or maybe in general we use friction stir welding process is the softer material, for example aluminum or aluminum alloy, and mainly based on welding of this alloy this process was developed, and now it has been advanced to application of relatively very hard material. So, in dissimilar material, but if we want to get a very good weld joint, in this case also we can reorient that position of the tool or maybe this thing external heat source. So, dissimilar materials is problematic welding because of two different thermophysical properties are completely different in these two materials, and if we can reduce the thermomechanical behavior of the material around the weld zone and with some optimum position of the friction stir welded tool as well as the secondary heat source, then it is possible to get a very good weld joint. So, that can be done in this two way. One, it is possible to that friction stir weld tool to offset any one of the side such that it can controls the volumetric mixing of the two materials and maybe some impact on the control of the intermetallic formation. At the same time, since thermal conductivity are very different for this dissimilar combination of the materials, then it is possible to offsetting the secondary heat source or secondary energy source relatively towards the high conductive material. For example, if we consider the dissimilar material joining between aluminum and copper, it is better to use the offsetting of the secondary heat source toward the copper side. So, in general, the advantage is like that: reduce the stresses of the tool, because external heat source actually makes the ease of material flow ahead of the FSW tool. So, that actually improves the stress on the tool, or indirectly the wear of the tool, or maybe it improves the life of the tool. That is the main significant advantage of hybrid friction stir welding process. But if you look into that, local heat source is used to preheat the relatively harder material either in similar or dissimilar combination, and prevents the formation of large amount of brittle intermediate compounds, and specifically for joining of the dissimilar material. That are the basic advantage of hybrid friction stir welding process. So, if we look into that other what is the main impact of the hybridization of the friction stir welding process is that it actually reduces the process load. So, then axial force actually reduces because by use of the external heat source in case of hybrid FSW process. And at the weld zone, this external heat source, of course, if we find the optimum combination of the offsetting in the tool as well as the secondary heat source, that actually reduce the difference of the flow stress. That means, it basically makes ease of movement of the tool, and in that way it helps to making a better weld joint at the interface. High conductive material, if one of the material is very high conductive for in case of dissimilar pair of materials, in that case recover heat, that means whatever amount of the generated heat will conducted away by the high conductive material, that lost amount of the heat can be recovered by using the secondary heat source. That is another purpose of using secondary heat source in case of dissimilar welding process. And offset actually controls offset for the FSW tool, that actually controls the intermetallic formation. So, these are the basic advantage of or impact of the hybrid friction stir welding process. But the secondary energy source can comes from two different way. One is the thermal energy assisted FSW, other is the mechanical energy assisted FSW. So, thermal energy FSW, that secondary source can be using some electricity, some induction, some laser, plasma, arc, hot gas flow or steam or gas torch, that can be used as a secondary heat source. But in this case, the optimization of parameter is very much significant, because finally the maximum temperature within the system should not cross the melting point temperature. So, therefore, careful using of this secondary heat source helps in case of thermal assisted friction stir welding process. So, the electricity and induction are used for the for basically resistant heating of the sample, and laser, gas or plasma source can be directly used to the substrate material for the preheating of the material. Mechanical energy assisted FSW, that only the ultrasonic energy is only the source of the so far has been developed for the mechanical energy employed for the purpose of the hybridization of the friction stir welding process. Actually, ultrasonic vibration directly sharpen the material by converting the mechanical energy and without much variation in the process temperature. So, that is the basic advantage of using some ultrasonic source, ultrasonic energy in FSW process. So, apart from the different technology or different FSW hybrid FSW process. So, now if we look into that specific to the friction stir welding of the dissimilar materials, what are the typical properties we observe in a dissimilar welded materials. In this case, we consider an example of joining of aluminum and copper. So, from the figure if we see that retreating advancing side is in copper and retreating side we generally put the aluminum, and exactly there is another trapezoidal zone, and that trapezoidal zone can also be considered as the zone corresponds to the functionally graded material, because at this point there is a mixing of the aluminum and copper exists in between these two. So, when we try to analyze the high bit fixed rolling process, we can divide the 3 different zone, and we can do the further analysis of that. So, here that formation of the functionally graded zone actually depends, it is actually transient in nature in the sense, because if you look into the fixed rolling process, the initially the plunging depth. So, we start from time t equal to 0 and gradually put the along the depth direction the pin, and that is in transient in nature, and then after plunging then we put some dual period also, and during the dual period the more or less the size of the functional zone can be decided, and then after that if we move forward, that means using some welding speed, then it creates the weld zone, but that weld zone is more or less uniformly formed. That means, at specific point the cross section is uniform and it gradually moves along the weld direction. So, that is why very initial period is transient in nature, and weld zone almost remains constant during this process. So, here if you see the typical that in the size of the functional graded material zone is like that, 1.12 of the shoulder diameter in the upper side, and the lower side 1.12 of the pin diameter. That means, just above the diameter of the pin size and diameter of the shoulder side in the upper side, that actually more or less creates that is the shape is like a triangular. So, this to analyze the hybridizing of the fixed rolling process specifically for dissimilar material. So, they create this kind of different kinds of the zone. Now, we can do in the further analysis of FSW of dissimilar materials, we can see that first figure shows this figure shows that highlighted part in the, that means, if we put the tool offset towards copper side, that means then this the mixing volume ratio during the fixed and rolling process between copper and aluminum, that actually as a function of the tool offset. So, if we increase the tool offset, that means volume ratio of volume of the aluminum is generally increases, and but as compared to the at the same time there is a reduction of the volume during at the mixture of copper reduces. So, that actually in that controlled by the amount of the tool offset. So, this way the looking into the volumetric mixing, that mixing ratio, if you look into this figure, that mixing ratio the copper by aluminum, that actually at the when the tool offset equal to 0, that means 100%, that means ratio is 100%, that means equal volume mixing exists at the tool offset of 0. But when the tool offset increases and it raised to around 2.5 tool offset 2.5 millimeter. So, the mixing ratio actually decreases, that means there is a variation of the mixing ratio. So, this way it is possible to control, and roughly we can estimate this volume mixing ratio, and that actually we can correlate the amount of the intermetallic compound formation just by simply controlling the amount of the tool offset. Also at the same time, here if we see that at the same time with the increasing of the tool offset. So, here the tool offset is provided towards the copper side, that means the tool is subjected to more resistance with the softer material as compared to the harder material. So, in that sense the amount of the axial force required decreases with increasing of the tool offset, because at the high tool offset very small part of the copper side is intact with the or contact with the tool as compared to the aluminum side. But whatever the tool we can use in general, the welding of the whether similar material or dissimilar material, the wear of the tool is the major concern, and that is the main component of the main concern of the industrial application of the FSW process. So, of course, in general the hardness of the tool should be much higher as compared to the workpiece material, and based on that there is a selection of the tool, and then accordingly the characterization or measurement of the wear during the friction during the FSW process, that is the one direction of work that needs to understand to completely find out the impact of the tool wear on the in general on the FSW process and their commercial use of that process. Even like other welding processes also, friction stir welding process also can create some defects, but that defects comes from mainly the improper choice of the parameter. So, extensive experiments are required to find out the process map of a successful weld joint. But if you look into that FSW process also, we can see that different types of defects can form. One is due to the reason of that improper material flow and heat generation. If heat generation are not proper and flow of the material is not very if certain part of the friction stir welded zone, if there is not sufficient material flow, that also creates some amount of the defect, and that defect is also influenced by the tool rotational speed. So, mainly tool rotational speed is the one most significant parameter that directly impact on the formation of the defect. So, normally tool rotational speed is very high to keep ensure that the sufficient amount of the heat generation during the interaction of the tool pin and tool shoulder with the workpiece material. Then tool traverse speeds, the welding speed is too high, that also creates some kind of the defect. That is why we can keep the very low traverse speed, we can ensure the low welding speed can be ensure the chances of reducing of the defect in friction stir welding process. Improper tool geometry selection. So, geometry is also another important parameter that actually impact on the formation of any defect. Sometimes the straight cylindrical or taper tool without any thread can cause the improper material flow. So, in that sense, adding of the thread on the tool pin profile can increase the material flow or material mixing. So, in that sense, that geometry of the tool is also another important parameter, and of course, that size of the pin, optimum size of the pin is also required. So, that you will be able to plasticize the certain part of the zone, so that it will be able to create some good weld bonding between the materials. So, insufficient flange depth is that may cause also welding defect. So, if flange depth is not almost up to the end of the bottom of the tool, that can create some problem also. Unequal thickness of the joining material. So, when there is a two different thickness material in butt joint configuration are joined. So, in that case it difference the thickness are different. So, the mixing of the then finding the optimum size of the tool is important parameter, so is an tedious job. So, in that sense they can create the defect if there is improper size of the pin. So, that is also another difficulty of joining, and there is a chances of producing some kind of the defect when you try to join the two different thickness material, and gap between the plates also impact on the defect formation in the weld joint, because if gap between the plates is too high, then the material flow may not cover up the gap. So, if it is possible, the optimum gap or maybe as close as possible to put the two materials is helpful to produce the weld joint without any defect. So, this with this we can conclude that friction stir welding process it is the one of the most significant development in recent days happens, and so much of work is going on fixed welding process, and now the direction of the work is going on the joining of the very hard material using the fixed welding process. The only reason behind this is that since this is a solid state process, so chances of formation of the other metallurgical or defects that normally happens in the fusion welding processes, but still for the several material aluminum or other little softer material, this fixed welding is an well established process. Now, come to the next topic, that is the diffusion bonding. This is another kind of bonding, solid state bonding mechanism. So, diffusion bonding is a solid state welding process. So, in these cases, that covalences of the two fairing surface happen by the application of the temperature and pressure, by the application of pressure, but under the environment of elevated temperature. That is the favorable condition to produce the diffusion bonding between the two surfaces. But the process, when you conduct this process diffusion bonding between the two surfaces, that actually does not produce any macroscopic deformation, but microscopic deformation definitely happens, and there is not required any relative motion between the workpiece. So, these are the criteria, based on that we can join the two surfaces. This technology or concept is very old, but still it is a very effective process. Sometimes a solid filler material can also be used, may or may not used between the fairing surfaces. So, right hand side we show the schematic figure of the diffusion bonding, that we can see the two different materials A and B. There is application of the force, and at the interface it is necessary to produce some amount of the heat generation. So, here electrical resistance can also be used to generate the heat at the fairing surface, so that two surfaces can be joined. If you look into the bonding mechanism in case of diffusion, so we can see that first stage is the deformation forming the interfacial boundary. If we see this is the actual contact, when the two surfaces come into the contact, they are in contact with the through the asperities between the into the contact. So, that there may be some gap between the asperities. So, then to make it flat, there is a necessary to the application of the pressure or application of the force. So, in the first stage, the deformation and interfacial boundary formation with the application of the force. Second stage, the grain boundary migration and the pore elimination. The grain boundary migration, so when there is a two surfaces are in contact, if we assume that contaminated layer or oxide layers are removed. So, in that sense, in after that they can, the second stage grain boundary migration can happen, and that there is a bonding form and between these two surfaces. And third stage, then overall bulk volume deformation happens and the pore elimination, it looks like a continuous surface. So, it is a continuous structure. So, that is the third stage, and diffusion pore elimination, that is the third stage is the stage volume diffusion and pore elimination, we can clearly see from the figure. So, this is first stage, second stage, and this is the third stage. Here it needs to mention also that diffusion bonding, the condition is that when it is a successful welding mechanism, but if it is possible to remove any contaminated oxide layers between the contact surface, then it is a very successful weld joint and it is a very good weld joint. And here only the process condition, that means process parameters is only the application of the force and over a certain time, over a long time, normally over a long time, and sometimes at the same time there is a generation of the heat is also required between the surfaces. These are the typical condition for the diffusion bonding of the metals. Now, if you look into that, which are the factors that actually influence the diffusion bonding or diffusion welding process, you can say that it needs to be two things are there. One is the temperature and time, how to relate in this process. So, temperature in the first case, if you see that d equal to d0 exponential minus q k t. So, d is actually diffusion coefficient, and we can see that diffusion coefficient is very strongly, that coefficient's value is very strongly dependent on the temperature. So, that is a function of temperature. So, d0 is the diffusion constant independent of the temperature, and normally we can assume that diffusion constant as a room temperature, and then the value actually varies with the exponentially decaying nature as a function of temperature. Here you can see. So, d0 is the diffusion constant, Q is the activation energy to start the thermally activated process, and then T is the absolute temperature and K is Boltzmann constant. So, with this nature the diffusion coefficients actually varies. Now, we can roughly estimate that what is the depth or length, what extent the diffusion bonding mechanism works basically. So, that is x, and that is a function of time also. So, here you can see the C is a constant and D is the diffusion coefficients and T is the time, and it depends on actually x is proportional to, basically depth is very much proportional to distribution coefficients and time. So, here x diffusion length or depth, you can see C is a one constant and D is the diffusion coefficients and T is the time. So, based on this equation we can find out of course, if we want to get the desired depth of penetration, then we can back calculate what is the time required for that, and of course, if we know that what are the temperature varies within that surface, then only we can decide the what is the value of the distribution coefficient. So, there these two parameters are the mainly, but just simple calculation, these two parameters are required in case of the diffusion welding. Now, as mentioned that if you look into the picture, the two surfaces, this is the typical configuration of metallic surface, that oxides and contaminated layer exist in the surface, it is there, and then this contaminated, for the diffusion bonding to be successful, this contaminated layer should be removed. So, that pure metal to metal contact will be there, and then diffusion mechanism will be very strong when there is a direct contact metal to metal without any metallic or contaminated layer. So, that is the only concern of a diffusion welding or diffusion bonding process. Application, we can find out the numerous application found the diffusion welding process. Application in the titanium welding for aerospace vehicles. So, titanium bonding, basically which material is very difficult or very hard material is very difficult to weld in other processes. In that case, probably the diffusion bonding is the another alternative method, and to get a good weld joint. Second one is the diffusion bonding of the nickel alloy also, that in, for example, in Cornell 600 they are also used for the diffusion bonding as well. And sometimes dissimilar metal combination, diffusion welding application, copper to titanium, copper to aluminum, to do the by looking into the dissimilar welding mechanism, we can join this dissimilar combination of the material. But even for dissimilar material, the main concern is the intermetallic compound formation, and that must be controlled in this application. So, in that sense, because the normally diffusion bonding mechanism normally takes very high time, time requirement is very high, and that we generally keep workpiece as a constant constant pressure for a long time, and during that time there is a high probability, or maybe probability is very high, because time for the formation of the intermetallic compound, because of the length of the time. Now, after diffusion welding, we look into another non-conventional welding process, that is called the explosive welding process. So, in explosive welding process, it is also a solid state welding metal joining process, and simply use the explosives, but in a very controlled way, so that explosive can create high impact of the one metal to the another metal, and then finally creates the metallurgical bond between the two surfaces. So, that is the basic principle of the explosive welding, and but the time duration or time requirement is very short during this process. It as opposed to the diffusion bonding, in this case the time requirement is very high to join the two surfaces, and since time requirement is very within the explosive happens, the high rate deformation happens over a short period of time. So, normally whatever heat is generated, that is in adiabatic, not having the sufficient time to diffused air or to convective air. So, if you look into the basic mechanism or basic process of the explosive welding from the figure, here you can see that the one substrate metal is there, and then plier we use, and that plier we are supposed to join that plier with the substrate material by controlled use of the explosives. So, normally the layer, this layer substrate material, then plier, and then chemical explosive. Normally in terms of powder we can put layer by layer. Now, if we can start from the one side the explosion, then it gradually start the using the chemical explosive and creates the explosion throughout the surface. So, it starts from this point and creates the explosive, and then up to that point explosive explosion happens, and then two surfaces are joined, and in between there is a high deform zone. So, that deform zone create, and that actually joined the, at that point the substrate and the plier are joined. So, normally the most common application of this explosive welding, we can find out the cladding carbon steel plate with a thin layer of the corrosion resistance material. So, we can use the stainless steel also as a corrosion resistance material. So, that we can find out the common application of that. So, here this red color actually indicates the chemical explosive that is arranged, and then explosion keep on going and moving in direction. So, that the joining between these two surfaces happens continuously. Let us look into that other aspects, the most significant aspects of this joining mechanism and explosive that observed in explosive welding, that is called jetting. So, jetting means during the explosion on the plier plate a high pressure pulse is generated. So, during the explosion there is a high pulse pressure is generated, and this pulse actually propels the pliers plate at the very high velocity, and the jet is then produced of the coalition of the two metallic surfaces, and the jet formation normally allows the two pure metallic surfaces to join under extremely high pressure. So, that means there is a high pressure pulse is generated during the explosion, and that is responsible for the creation of the jetting. Now, the welding, whether we can say the welding depends on the piece of the metal plate that collides at what angle with respect to the parent metal plate. So, that angle is also important, and that is related to the jetting mechanism. So, for welding to occur, a jetting action is required at the coalition surface, then only the weld can form. We can see that what is the process geometry of explosive welding. See, the parallel plate bonding is used for the large plates. So, for the large plates, two parallel plates can be used, and the plier plate velocity range from 250 to 500 meter per second, that is the plier plate velocity, and exactly at which point with the application of the explosives, that coalition point velocity range from 1500 to 3000 meter per second, that is very huge velocity. And then angle is also an important parameter. So, angle is around 2 to 20 degree. So, the impact must be sufficiently high to that to cause the colliding material surfaces to flow hydrodynamically when the initially contact, when they are intimately contact with respect to each other. So, that hydrodynamic flow of the material during the explosive actually occurs, and then only welding will occur. If we look back to the picture also, that so here if you see that this deformed metal already deformed metal, this part, and this is a substrate metal. So, this is normally thicker as compared to the substrate material, and if we create the explosive, it is directly joined with this substrate material. So, that there is a, but this process happens in a very small period of time, and then after joining these things, this can be compared is like a cladding process, just one layer is attached with the substrate material. So, that cladding layer normally we can use the some that having the corrosive resistance material. So, that in that way it is used, or you can call is as a welding process, explosive welding process. So, you can see that these are the typical parameters of the explosive welding process. Now, steps in the wave formation and the bond morphology. First is the impact by the explosive actually produces some shear deformation, and that shear deformation in the stationary base plate, which results is actually depression. So, that it causes in such a way that it actually creates the kind of hump during the using continuous use of the explosive, or the explosive that explosion actually moves one certain direction, and then creates the kind of hump and they join, and then hump interfaces with the, at the same time when the hump interfaces with the jet flow, and that actually produce some kind of the eddy in the within the jet. So, that creates actually the coalition point velocity constitutes a forward deformation of the hump, and the further jet creates some turbulence, which again causes the jet entrapment in the front vortex. So, that means this is a complex phenomena with the application of the fairing surface kind of hump. At the same time, there is a jetting phenomena, they interact with respect to each other and create some eddy, and or of course, that has impact on the jet turbulence as well. So, these are the typical steps, and then after doing all these things, then finally, it creates the bonding mechanism between the two surfaces. So, it is simply the mechanism is the basic high strain rate plastic deformation of the metals, and that is responsible for the bonding between the two surfaces. So, explosive bonding, if we look into the theoretical aspects of the wave formation and the coalition, we can find out some simple calculation for that. That if we assume the Newtonian liquids, that flow streams of a Newtonian liquids, and then we can assume that the flat plate of the elastic plastic solid, and then we can typical observed boundary wavy bond zone. So, at the boundary we can say not very straight zone, it is a kind of wavy bond zone we can find out on the boundary between the two surfaces. And here the angle, the dynamic bend angle, that is also important parameter. So, we can empirically estimate the dynamic bend angle like that, B beta mean equal to K H B by rho V c square. Actually, H B is the flare plate hardness. So, the beta, that means that angle, dynamic bend angle depends on the hardness of the flare surface, directly proportional to that, and also at the same time it depends on the density of the flare surface as well as the coalition point velocity. So, velocity is also another important parameter, hardness and density, these are the parameters that actually decides the amount of the bend angle, and this is empirically, and definitely K is constant here. So, velocity calculation can also be done that shock wave propagation, in the principle during the process is that shock wave propagation should exceed the sonic velocity, means the what is the sound velocity within that medium, that means with the that metal. So, it should shock wave should propagate more faster than that of the sound velocity. So, most metals have the sonic velocity from 2000 to 6000 meter per second, that is the data, and explosive velocity is actually greater than 120% of the sonic velocity of the material, also should not be used, because it definitely the shock wave propagation velocity should exceed the sonic velocity, but it should not exceed the 120% of the sonic velocity, because at this point the deleterious effect of the shock rarefication may also happen in this case. So, sonic velocity of the material, simply we can calculate the simply square root of E by rho, that means E is the elastic modulus, rho is the density of the materials and V s is the sonic velocity. So, these are the typical velocity estimation can also be done. Other component of the detonation velocity, it is also one kind of characteristic type of explosive. A characteristics type of explosive has been shown to be directly proportional to the explosive density. So, detonation velocity is exactly depends on the density of the density of the explosives. So, for I think nitro guanidine explosive, it ranges from 2000 to 5000 meters per centigrade. So, this is the one type of explosive. In this case, the velocity actually ranges from 2000 to 5000 meter per second, and the density is around 0.14 to 0.9 gram per centimeter cube. So, using this specific explosive, the detonation velocity is around, we can empirically relate the 1440 plus 4020 into rho e. That means, we can see that it actually depends, linear dependence of this detonation velocity actually linearly depend on the density of the explosive. So, flare plate velocity can also be estimated from here also, and here you can see that V d, that flare plate velocity is also depends on the detonation velocity, and sin beta by 2, and beta is the that angle we have just calculated, that beta equal to the minimum dynamic bend angle. So, beta is the dynamic bend angle. So, we can put the beta, if you know the beta value. So, then we can find out that flare plate velocity. This is the just some analytical estimation of this, the order of velocity we generally find out in the explosive welding process. So, explosive pressure also depends on the that flare plate velocity and the density of the explosive. So, these are the typical calculation we can in case of explosive welding. Now, we come to another non-conventional welding process, also you can say the electromagnetic pulse welding process, and in this case the electromagnetic pulse welding process, here is the Ampere's law is used, and because if you current carrying conductors, if you use it, then there is a magnetic force actually force field actually created with the application of the current field. Now, if you know that the force between the two infinitely long parallel conductor is given by F equal to mu 0 by twice pi d I 1 I 2. Actually, the mu 0 equal to permeability of the free space, d distance between these two conductor, and I 1 I 2 is the current flow. So, based on that we can find out the force between these two parallel conductor. So, then if we apply the Lorentz force, that is F equal to the cross product of the current density as well as the magnetic flux vector. So, based on that we can find out the Lorentz force. So, that means electromagnetic pulse welding is just flowing of the electric current, and there is a magnetic force field, but if we can use that magnetic force field actually depends on the current density and the magnetic flux. So, this principle of producing the magnetic force field, and that can be used in a controlled way. So, it is possible to develop the welding that based on that the development of the electromagnetic pulse welding has done. So, here you can see the welding process, the energy, normally in the electromagnetic pulse welding process, the energy stored in the capacitor bank and then charged through a DC power supply. Then energy is discharged through the work coil by triggering the spark gap, and then damped sinusoidal current set up in the work coil produces a transient magnetic field, because that is why here with the application of the current field it can create the transient magnetic field, and that transient magnetic field is basically created around very small time span, around 50 seconds, and this is sufficient to produce the joining of the two materials. But if we see that transient magnetic field is responsible, that here the induced electromagnetic force and the corresponding eddy currents in the worksheets oppose their causes, and therefore, the induced eddy current actually depend upon the material properties, that means conductivity and permeability of the material, and based on that the induced eddy current actually develop. Finally, the work sheets are repelled with respect to the away from the coil towards with respect to each other, and then creating an impact due to the Lorentz force, and that happens over a few microsecond. So, therefore, on account of the interaction between the induced eddy current and the magnetic fields, all actually this impacting of the one metal to other metal actually happens, and that happens over the very short period of the time. So, therefore, we can see that like explosive welding also, the electromagnetic welding also happens, it is a very small period of time. The bonding mechanism is that here also jetting action occur due to the high velocity impact and causes that high impact, but at that time the expulsion of the oxides layer and contaminated surfaces that first clears, and then after that sheet metals can be joined. So, after the collision, the automatically already clean work surface come into the contact, and they can contact at very high pressure, and then they can join by this electromagnetic pressure. So, therefore, the weld is formed at the interface by establishing the metallurgical continuity. So, what are the typical parameter for electromagnetic pulse welding? The process parameter, that inductance of the current, that is the one significant parameter, frequency, capacitor bank energy, voltage, current, and the stand-off distance between the sheets. So, you can say the electromagnetic pulse welding is more suitable for, normally we can join between the very thin sheets, because the creation of the electromagnetic pulse or electromagnetic force field over a short period of time, that also having some limitations. So, therefore, in practically we generally use the electromagnetic pulse welding for joining of the sheet, two different sheet, and we can use also the two different geometric configuration, that means two different sheet pipes. So, normally thickness of the pipes is less, so that can also be joined using the electromagnetic pulse welding. So, application we can find out electromagnetic pulse welding, that magnetic pulse welding is used more applicable to tubular structure than the flat sheet. So, tubular structure is more useful to joining using this electromagnetic pulse welding. So, mechanical joining of the tubular cross section, and torque rods is also already in use for the high volume production. So, therefore, joining of the tubular cross section already implemented the electromagnetic pulse welding process. Normally, this process is very much suitable for the underwater application and automotive spare frames. Joining of aluminum cans and the cap wafers to avoid heat generated problems that actually encountered in the other arc welding processes. So, in that case the electromagnetic pulse welding is very advantageous. It is also one thing is that in electromagnetic pulse welding, that here also we need the electric current. So, it is also one kind of we can say that it is a green technology, because there is no fumes, no gas produced during the process itself, and it is a environment friendly process as well. So, this process can also be used welding of dissimilar materials also, or specifically dissimilar tubes. Bimetallic materials can also be joined, and specifically lightweight. So, normally this process has been developed for softer aluminum based alloy for electromagnetic pulse welding, and of course, it is having some nuclear projects to join reactor tube to ceramic plug. In that particular application, we can find out the electromagnetic pulse welding process. So, we have discussed in this solid state welding process, apart from conventional welding process, we can say that some other non-conventional machining process, just as the explosive welding process, electromagnetic pulse welding process, these are the typical development of the solid state welding process apart from the fixed state welding process. So, out of this all this process, there is a huge development happens, or still work is going on in fixed state welding process, but till other non-conventional processes is also applicable for when there is a limitation of the welding, specifically for the tubular structure and specifically for the dissimilar combination of the materials. So, other welding processes are more conventionally used. So, in summary you can say that first we have discussed that solid state bonding mechanism. So, solid state bonding mechanism, here we cover up that localized melting mechanism, diffusion mechanism, recrystallization, that is also one kind of mechanism that is responsible for solid state bonding, addition, that means joining of the two surfaces by additives, then interfacial reaction, then interfacial morphology. Interfacial morphology means that joining of the high rate of deformation that normally found out in the explosive welding and electromagnetic pulse welding. These are the typical mechanism is responsible for the solid state bonding mechanism. Then we have discussed that cold welding and ultrasonic welding, cold welding process during the upsetting joining of the two materials with the application of the pressure, and then ultrasonic using the vibration energy, that means mechanical energy. Here we can join the two metals also, and of course, the ultrasonic welding, very thin sheet is applicable for ultrasonic welding process. Then we have discussion a lot on friction stir welding process, specific for similar kind of material, dissimilar material process, and what are the recent development of the friction stir welding process. That means, in terms of hybridizing of the friction stir welding process to get certain advantage of joining different dissimilar combination of the materials or similar combination of the materials. Then we discussed the diffusion bonding also, the diffusion bonding, the joining of the two metallic surface with the application of the pressure and temperature, but normally diffusion bonding takes a long time, and in that sense the explosive welding and electromagnetic pulse welding, that also happens, the high rate of deformation happens but over a short period of time, that deformation of the at the interface zone, high rate of deformation interface zone creates the some bonding mechanism between the two surfaces. So, here also explosive welding, electromagnetic welding, that actually the flare surface or faying surface, that actually we normally use is the very thin sheet to get the successful weld joint using these two welding processes. So, this I can conclude that end of module 3. So, thank you very much for your kind attention.